Yes, hello everyone. It's really nice to have you on this webinar. You can see our presentation for today's webinar. So again, I would like to very nicely welcome you on this first webinar of minerals. And the title of this webinar is Critical Metals Extraction Processes for a Greener Future. And this is the MDPI series of webinars. And as I already told you, this is the first webinar of Minerals Journal. And MDPI is the open access publisher. We were founded in 1996. And we have headquarters in Basel, Switzerland. And right now we have more than 400 diverse and open access journals. And the disciplines are very different. So you can see our full portfolio at our website at mdpi.com. And today's webinar is organized on behalf of the journal Minerals. Journal Minerals is international peer-reviewed open access journal of mineral systems and a very broad topic on the mineral science. We are indexed in many different scientific databases like Web of Science, also Scopus, and we are also ranked in Q2 category. This is mining and mineral processing, and also in Q1 category as of site score in geology. And the impact factor is 2.2, and the site score is 4.4. So now I would like to briefly introduce you with the agenda of the webinar today. So first we will have the short introduction from our chairs, Dr. Hamilton Barbosa Botelho Jr. and Dr. Rogerio Navarro. Then we will have three speakers, Mr. Gabriel Medeiros, Professor Eduardo Junca, and Dr. Carlos Oba. And afterwards, we will have the Q&A session. And after that, we will be closing the webinar with a few words from the chairs and me. And I also would like to mention that this webinar is organized in cooperation with the special issue entitled New Extraction Processes for Critical Metals from Non-Metallurgical Resources. And the chairs of this webinar also serve as guest editors of this special issue. So Dr. Rogerio Navarro and Dr. Hamilton Barbosa Botelho Jr. The deadline for submissions is the end of January next year, 2026. And if you would like to see more information about the special issue, you can visit our website. Also, Chair, Dr. Hamilton, would you like to add some few words about the special issue now?
Thank you so much. Yeah, we are looking for outstanding works in recycling, mining waste treatment, and critical minerals recovery due to the importance of those materials for energy transition. So the best papers we are going to be submitted. We are going to deliver 100% discount voucher for publication. So be open and submit your paper because we're looking for to receive the best papers in this area. So thank you so much.
Thank you very much, Dr. Hamilton. And here I would like to mention that the Q&A session will be held after all of the presentations. And in the bottom panel of this window, you have the Q&A session chat. So if any one of you would like to ask a question, please write down your question in the Q&A chat box. And please remember to put the name of the speaker to whom you would like to ask the question. And during the Q&A session, we will try to answer these inquiries. So now I would just like to briefly introduce the people we have on this webinar. So the chair of this webinar is Dr. Hamilton Barbosa Botelho Jr. from Department of Materials Science and Engineering from Massachusetts Institute of Technology in Cambridge in US. Then we have the second chair of this webinar, Dr. Rogerio Navarro from Chemical and Materials Engineering Department from Pontifical Catholic University of Rio de Janeiro in Brazil. And we have three speakers. The first one is Mr. Gabriel Medeiros from Chemical and Materials Engineering Department, the same university, Pontifical Catholic University of Rio de Janeiro in Brazil. The second speaker is Professor Eduardo Junca from Postgraduate Program in Materials Science and Engineering at UNESCO, Brazil. And the last speaker is Dr. Carlos Oba from Department of Mining and Petroleum Engineering at USP in Brazil. And now I would like to give the voice to our chairs. If you could very briefly introduce the topic of the webinar and present the first speaker.
Thank you so much for this opportunity. It's a pleasure to be here again and hosting this webinar. MDPI has outstanding publications and minerals journal. It's delivering a lot of really good really good publications in terms of critical materials, critical minerals extraction and recovery towards the energy transition. Our special topic is delivering the outstanding research in this field, and it's a pleasure to be here again. Rogerio, would you like to say a few words?
Yeah, just a few words. I'd like also to thank especially the Minerals Journal for this opportunity. For me, it's an honor to be here as co-chair in this webinar, and also to praise the initiative of simulating the exchange of research in an area which, on my opinion, is vital for the future development of the mankind. Yes, because we are seeing an urgent situation regarding the climate change, and is inevitable to think that both metallurgical and minerals industry have contributed to that. So I think that is mandatory in this moment to think of new and greener strategies and look for treating materials which are like slags, e-waste, mineral waste. So this type of material, which we know that they are complex regarding the chemical nature, but actually they are sources of important metals which are vital for the technological development of the mankind, as I said. And yeah, it's very important to say also that we are ready to face this challenge, although it's a technological challenge, in my opinion, naturally, because we have accumulated a lot of knowledge, especially regarding phenomenological modeling of the reactions and physical process involved in the metal extraction from mineral resources. So I think also that the materials characterization tools have also evolved a lot. So we are prepared to face this challenge. So it's very nice to be here today to discuss this topic with you. And I like to especially thank all the speakers, all the scholars that have contributed to this event with their presentations. Thank you very much. Thank you, Hamilton. And I think that we can jump into the presentations. Thank you, Agnieszka.
Thank you. So I'd like to invite Mr. Gabriel Medeiros. He's going to talk about non-ferrous recovery of EAF steelmaking. So Gabriel, thank you so much for having us here, for having you here, and the floor is yours.
Okay, thank you for the opportunity. I hope I can contribute with you. And I'm always anxious for my colleagues' presentation. Let me share the screen. So I will talk to you about non-ferrous recovery on this specific steelmaking route, which is electric arc furnace route, and how recycling is an effective alternative environmentally to the extraction methods and complementary to the extraction methods. So this is the basic agenda. We have a brief introduction about steelmaking and its roots, And then we come to recycling, scrap, and non-ferrous content on scrap. And at the end, we'll talk about eddy current separation, which is the main technique I will bring to you today for non-ferrous separation. And then the characterization of this product and how it's sold and traded on the market. And just as a background, we see on the last decades the steel production rise, mainly driven by the capacity of China. But the fact is, steel is very important to the society growth, and making this route more sustainable and get additional circularities on the value chain is a key factor to make the steel making routes better to the future. So here we have on the left basic routes for steel making. So we have down on the figure the classic route with blast furnace, the most famous one from the iron ore and metallurgical cokes. Then it comes to refining the steel and make the final product, which can be slags, blooms, or billets, depending on the shape. But we have also an alternative route, which is electric arc furnace. And the electric arc furnace was made to recycle steel scrap. That was the concept from the beginning of this process. But nowadays, it's being explored a new route, which is direct reduction coupled with electric arc furnace. And it's very interesting because besides the recycling, you can extract the iron from ore in a more sustainable way. When I talk about this, I talk about energy intensity and also CO2 emissions. I bring to you here today the CO2 emissions just for example, but we have the DRI coupled with EAF routes with almost a half of the emissions of CO2 when compared to classic blast furnace routes. And if I'm talking about scrap EAF with no ore, it's even lower. So it's a very interesting process, and it's been growing in the last years, and it must grow even more in the next ones as a sustainable steel making route. Now it's like 30% of the global production. It's the 2024 data, okay? So how is this scrap on the value chain? I bring you the graphic that forecasts the end of life scrap viability. And of course, as the society consumes more, it generates more scraps. I mean, scraps like cars, old bicycles, old refrigerators, and other goods we consume every day. So use better and extract the better for this scrap is also crucial for the recycling route. But what is this scrap? Of course, it's not only steel. We have the coats, the paints, the oil, the dirt, the rubber. I mean, if we think about a car, we have a tire, for example. We have a lot of plastics nowadays. But we also have a lot of non-ferrous contents, metallic non-ferrous contents. So it's a good challenge to think on the steelmaking routes, creating an alternative route to non-ferrous recovery. That's what I'm talking here today. For example, aluminum, copper from electric motors, all of these are mixed on the steel scrap. Additionally, we have the tendency of many metals and minerals to be in lower concentrations along the years on the mines. And then we have to work even harder on the extraction methods, but we must also recycle more. But just to detail a little bit more the non-ferrous, I talk a little bit, but I bring here the comparison between an old Beetle from the 60s and a Prius from the 2025. The old car has a lot of steel combustion engine made by cast iron, no electronics on board. And on the other side, we have an hybrid electric vehicle with an electric engine, combustion engine that is made basically by aluminum and not a cast iron anymore. A lot of other aluminum parts on the body and the structure mixed with the steel. And this why I bring cars, because it's of course a huge generation of this kind of scrap all over the world. So given this, it's very clear that we must have appropriate methods to separate these other materials and bring value to them on the value chain. To give an idea, it's a forecast of electric vehicles, hybrid or electric, pure electric vehicles, and its copper consumption along the years. As I said, it's a forecast, but it's already happening. So we have every year less combustion engines, more hybrid, more electric, more copper consumption, and also more scrap generation from these vehicles. I mean, batteries, motors, electronics, and all these things. So it's a very promising route for the future of the recycling. There is a great equipment on the scrap route for steel making. That's the shredder, and the shredder was fought in the past just to crush the scrap and make it smaller to put on the electric arc furnace and make the melting viable. That's the basic concept of the shredder, but it's not only this. It have also magnetic separation, a magnetic drum to separate the ferrous materials. And on the last years, it's been coupled with an eddy current. That's a technology I will talk more on the next slides. But what's the basic function of the eddy current? Is to separate the non-ferrous from the other non-metallic, using the conductivity as the crucial property to this separation. We have also an idea of the mass balance. Here, there are 3 mega shredders together. So all over the year, more than 1 million tons produced. And it gives you like 11,000 of non-ferrous. So it's not so small. It can give a good amount of recycling for these metals and even a good revenue. This is just to make it more viewable. It's a typical idea of a shredder plant. So we have on the left the feeding of the shredder. Next, we pass to the crushing machine, the magnetic drums. We have the ferrous separation, and then we have the eddy current series. Why I say series? Because we can have 1, 2, 3, 4 eddy currents as we intend to separate better these metals and with finer fractions also. So I can couple more eddy currents on this equipment to make it more efficient also. So it's a very flexible route. Here on the left, we have a view, a schematic view of the principal rotor, where you crush the scraps. And on the right, we have the magnetic drum. This is very simple. It separates iron from others by magnetic attraction, okay? It's not complex technology. But then you have the eddy current. That's the interesting part. What is the basic concept of this equipment? You have an alternating field, an alternating magnetic field that induces an electric current on the conductive material, a non-ferrous metals on this case. What happens that this induced current interacts with this field and creates a Lorentz force, and also gives kinetic energy to the particles. So we can have this kind of simple separation because we basically levitate and accelerate the conductive metals, and the other materials no, so they fall immediately on the first box. So it's a very curious and interesting technology. On the left is the basic one made by a permanent magnet assembled inside a rotating drum. So it creates the alternating magnetic field. But newer proposals of technology intend to do the same with an electromagnetic coil, not a permanent magnet, with an alternating current with a specific frequency. And the concept and the effect over the material is the same. It creates kinetic energy and provides the separation of this material. So this is the main concept of this separation. So the flow chart can be as complex as this, or even more. So you have the shredder coming to the duster. It's called the Z-box here, but the function is to collect the light waste. Then magnetic drum, you have the shreds, the main steel scrap to be consumed on the steel making route. And then we go with this overband to a sequence of screeners and size separations coupled with eddy currents. Depending on the size, we have the large Zorba, the medium Zorba, the small Zorba. Zorba is the commercial name of this non-ferrous product. Why do we have a commercial name? Because it's a mix of non-ferrous. All right, so it's not a pure aluminum, pure copper, pure. No, it's a mix of this that must be characterized to be sold. And that's the point I will talk now about the characterization of this product to being a commercial valuable product. So I have here the definition of Institute of Scrap Recycling Industry of North America. And it basically says that shredder non-ferrous scrap is a mix of non-ferrous. It mentions some of them, as I told you. And it also says that the composition of this material can be and must be agreed between the seller and the buyer. And so it gives flexibility on the price and on the material characteristics. So you can sell different composition materials depending on the efficiency of your process, and also depending on the scrap input you have. And it also mentions the commercial name. So, for example, Zorba 90, it means that's a non-ferrous shred scrap with 9% of aluminum, approximately, okay? And it's very interesting because on characterization, we also think about very complex methods, but it must be an industrial one. This method, this classic method, is very visual. So we have a amount of this scrap. We separate the electronic boards, I can say, the electronic parts. We separate the waste, and the metals are collected associated with the colors. So we have the red metals. It's a common name on the industry. It's basically copper alloys. The brass are called the yellow metals, and the gray-white metals, which basically aluminum and stainless steel. And the interesting, you can separate it also by density, because aluminum is much lighter than stainless steel. On this slide, we have a real sample. It's not a determination of value. It's just a sample. It can be different on different shredders depending on the equipment and also the scrap. It's just a reference, but the seller must show this to the buyer, of course, to agree the price. And here we have an example of a small Zorba, which contains more copper and brass on this case, but it could contain more aluminum in some cases. And also a large Zorba here with almost 90% of aluminum. Just to show you, we have an average here of price in North America of this material. It's almost $0.50 per pound. So, as I said, it's also a good revenue to the steel making production industries. So, just to close, some highlights. It's very important to have these alternative recycling methods. It's crucial to deal with the demands and also to deal with the natural resources. So I think it has a lot to do with the sustainability of metal industries. Recycling is also much less energy demanding. I give you the example of steel, but you have also the example of aluminum. We can have a 95% of reduction on energy intensity when you compare the extraction with recycling. And there's circularity on the steel recycling route is very interesting to enhance and improve this value chain for the sustainable future. In here presented one of the great things of this, which is the non-ferrous separations on eddy current methods. But in general, we must see the metal value chain with these opportunities, not only what I want to produce, but what I can get more from my roots. What is the side material, the co-products that I can have on this value chain? Oh, some reference I brought here on the presentation, just to know. And that's it. That's my contacts, my emails, and I'm closing here. I think I got the time of 20 minutes.
Thank you, Gabriel. Thank you so much. Yeah, just in time as a British clock. Thank you so much for your presentation. I'd like to invite Professor Eduardo Junca. Eduardo Junca, it's a pleasure you are here with us. And for me, it's more than a pleasure because we did master's and PhD in the same laboratory in Brazil. So it's more than a pleasure. It's an honor have you here. So the floor is yours.
Hello, everybody. It's nice to meet you, everyone. I will show you like 1 minute, please. First, I have to say thank you for Milton, and Professor Navarro for the invitation. It's a pleasure for me here. Presentation, a piece of my work here in UNESCO. UNESCO is it's a university in Santa Catarina State. Before I start I have to say thanks for the FAPESC. FAPESC is a foundation that is financing this project that I will present for you now. So I decided to present a work that we are developing here. It's a PhD thesis. We don't finish yet, but we have good results, interesting results. So that I think it's going to be good present to show you for you guys these results. So I will present something about the alternative routes for niobium oxide extraction. I would say it's a work that we are developing here at this moment. My name is Eduardo Junca. This is my email. You can send email for me anytime. I see on the chat we have several people around the world watching this presentation, so feel free to send message for me another time. It's a pleasure to change information. I don't have a problem about this. You can send email anytime. So my email is eduardojunca@unesco.net. I don't know if the presentation will send for the people, but if for me it's okay, or Milton, okay. If you want someone ask you can send. So, niobium oxide. Everybody knows the niobium oxide. It's a good metal for several applications. For example, capacitors, solar cells, aerospace, and the Brazil is the biggest producer of niobium from the world. About 90% of global niobium production is from Brazil. So this is the point that we start to study niobium here in my university. It's a line that I am studying at this moment. So the challenge, we research about the niobium extraction. We see the use of some critical materials, for example, acid, hydrofluoric acid, hydrochloric acid, for example, sulfuric acid. We think, well, we can develop another route that we don't need to use this method. So let's go try something different to extraction niobium oxide from the rock. Okay, this was the first point. So we start to read some books, some papers. You decide to, okay, let's go study something to remove this niobium oxide using, for example, something that contains sodium and boron. Okay, this was the first step, first idea when you start the project. So we start to looking for materials. We decide to use então sodium carbonate as source of sodium oxide plus boric acid as source of boron oxide. We prepare some mixtures about these materials. So let me put it here. Okay, it's better. We studied several compositions with these materials in order to obtain in the final of the process some concentration of niobium oxide. This was the goal of the project, okay? So here I present some a resume about the method that you used. As raw materials, use 3 raw materials. Columbite was the source of niobium. Sodium carbonate as source of sodium oxide, and the boron acid as source of boron oxide. We also developed a design of experiment in order to obtain result. What's the best result to obtain a concentration of niobium oxide from the relation from sodium oxide and boron oxide. What's the point? So we made a design of experiment in order to optimize this ratio. Then we perform a fusion, magnetic separation. Then we develop a water solubilization. This point is the phase formed in this route contain phase niobium phase solution in water. So we made this step in order to study the effect of temperature, time, and the sodium and liquid ratio in order to maximize the extraction of niobium from the after the fusion. So as we have the niobium in water, you need to precipitate this niobium. So you study a route using guanidinium carbonate. Then we need to calcination, the product obtained here in this step, in order to obtain the niobium oxide. So the good point is the final result is niobium oxide. This was a good point. So, but as it is the first study about using this route, we have a lot of questions yet. We are in this moment, the project don't finish yet, so you have some time to investigate more. Well, the first point is what the composition, what is the ratio between sodium oxide and boron oxide you have to use. So we made some preliminary tests in order to investigate which ratio between those elements we have to start. After several experiments, preliminary tests, we see visual. I will show a movie about the fusion step. We decide this point A, is the first one. Then we decided another point B. We use this point B? It is an eutectic point. It is a low temperature between sodium oxide and boron oxide. Okay, it's important to decrease the temperature for the industry. Okay, but well, you can ask, well, but we have another eutectic point here, right? But if you use just here, point A, the point B is just here, the range of the niobium oxide, sodium oxide and boron oxide is so narrow. So you can have some problem to investigate what's going on if you change this relationship, the relation of these materials. So you decide to put this point, and you use this point in the design of experimental 2. So you have this point 1A, the point B, and this eutectic point you also put in the design of experiment. Okay, so the range was between this point, you see these points, this area in my study. So here I show you the formulation you used in the first step, the fusion step. So for you guys understand better, né? The letter C means the columbite. The number 10 means the percent of columbite used in this formulation. And A means the sodium carbonate. 81, the percent of sodium carbonate used in the formulation. And the letter B means the boric acid. And the number 9 means the percent of boron acid used in the experiment. So you can see that the columbite percent was between 10 to 20. The sodium carbonate, the range was 81 to 68%, and the boron boric acid was around 9 to 12%. Okay, you decide to use this. It's from this phase diagram. And the columbite, you looking for some papers. You see, I see some papers that use this percent in the study. So you decide to use the same percent of columbite. Here you can see a move about the diffusion process. Okay, here's the furnace. This is a vessel contain water. So diffusion was carried out at 900 degrees Celsius. The time for diffusion was 60 minutes. It's important. After diffusion, the molten materials was cooled in water. The temperature is environment temperature. In Brazil, so high, but it's okay. So after the diffusion, the metal, the formulation, we turn on the furnace, turn off the furnace, and the melt formulation dripping to the vessel contain water. Okay, just to cool the liquid, just for it. Then we perform a magnetic separation. Just to see because the columbite contain iron, so we try to perform this step to see if the separation magnetic separation can remove some materials in my process. Okay, so the magnetic separation was calculated. The percent of the magnetic materials was calculated about this expression. So the mass of materials is a relation between the magnetic materials and the initial sample mass. Then the magnetic separation, we dry the materials in order to characterization by ICP and X-ray diffraction. It's important to say, in all steps, we perform this step. In all steps, we dried the products, all products we dried, and we perform the characterization by ICP and X-ray diffraction. We don't have all results yet, but we have some results. I will show next. Then after the magnetic separation and dry the materials, we have a powder. we need to study, so we study the solubilization of the materials obtained after diffusion in water. So in this step, we made a new design of experiment using three variables. We study the effect of temperature, time, and solid and liquid ratio. Okay, so the temperature that we studied was 30 degrees Celsius until 80 degrees Celsius. Time, we studied time between 1 hour to 3 hours. The solid liquid ratio is 110 to 150 relation. We have two central points in this program, experimental program. Is the middle point for temperature, time, and ratio. What mean? For example, temperature I use from 30 to 80 degrees Celsius. The middle point is the average between this temperature, so 55 degrees Celsius. The time, the same thing. I use 1 hour to 3 hours. The middle point is 2 hours. It's the same thing for the solid liquid ratio. The low was 110 and after up to 1 to 50. So the middle point is 1 for 30. It's very simple. Using this technique, we can study the statistical to find what the parameters was better or have influence for the extraction of the metals. In this case, the niobium oxide. Okay, then we have the niobium oxide in water, so you have to precipitate, remove this niobium oxide from the water. How you can do this? We found an interesting materials called guanidine carbonate. You can see the equation here. As the product is niobium oxide with another things here. Carbon, nitrogen. So the important thing is the final products contain niobium and tantalum oxide. So remember that in all steps we perform the dry to obtain a powder, okay? So we prepare, the precipitation was using 15 grams of solubilized sample in the previous step in 1 liter of water. We keep this set in shake for 30 minutes. We put into this set 20 grams of guanidine carbonate. So we have two phases, a solid and a liquid. The solid phases contain the niobium oxide. So you have to separate the liquid and the solid phase by filtration. Then the solid phase was dried for 100 degrees Celsius for 24 hours. And again, we perform the characterization by ICP and X-ray in both materials, in the liquid and the solid fraction. Remember, again, we dried everything. It was just a method for us. We can perform the ICP with the liquid obtained here, but we prefer dried, weight a mass, and preparation a specific sample to send it to characterization. It's just a method for us. The calcination, well, the solid phase obtained in previous step was sent to calcination step. We use just a furnace at the 900 degrees Celsius for 60 minutes. And the product obtained in this step was again sent for characterization by X-ray and scanning electron microscope. Well, I did put here the ICP results because we don't have this result yet. We sent for the analysis, but I don't have the result yet. So I did put it here. Well, results. We start the characterization of the columbite ore. We can see here the chemical analysis is the main element is niobium oxide. We can see here tantalum oxide and iron oxide. These elements are the main elements present in the columbite iron ore. The X-ray show that the ore is columbite. You have some trace, a little zirconium phase also. Okay, some results of fusion. We see that the boric acid reduces the fusion temperature and viscosity of. This is obvious because the acid boric is a flux materials, but it was interesting because we see that boric acid was essential for extraction efficiency because this characteristic, the boric reduces the temperature and viscosity. The niobium oxide is free, I can say this, to react with sodium to form soluble phases to remove in steps of this process. We two formulations was the best presented best results. The formulation contain 69.5% of sodium carbonate, and 10.5% of boron acid, using 20% of columbite. This one was a good point too, a good result too. But the results that I will show you now is the result from this formulation. Okay, so the boron acid present good results, so you have to research more about this. It's just a first work that we are developing here, and the good point is good results. We found out good results. Here is the water solubilization results. We can see here the statistical results analysis. We can see that the solid ratio was the only this variable was significance. The temperature and time, they have significant statistical significance here. We can see by pie diagram a negative influence. What does this mean? This means that if I increase the solid and decrease the liquid phase, this has negative influence on destruction of niobium in this step, in the water solubilization. So in temperature in time, we can see a p-value higher than 0.05. So this did have significance statistical. The point is, this result shows that we have 95% of certain that the solid and liquid ratio is influence the process. In resume, it's this point that this result shows. This soluble phases we found. I should show it the next slide. Was here, we can see here, is sodium niobium oxide. All of those five phases are soluble in water. Is important. For the next step, we can remove by precipitation. So we perform the precipitation. Precipitation of using guanidinium carbonate. The best result. So after calcination, precipitation calcination, we obtain predominantly niobium oxide. I will show you for you guys the X-ray analysis and the same analysis. And the another one, I show Lewis-Schitt phase. It's different phases. We don't have 100% certain what's going on here. Why we obtain niobium oxide in this one, and why we got Lewis-Schitt in this step. My thesis for this is that the excess of sodium can generate this difference, but we don't have 100% certain about this. We have to do some research about this. We are doing this at this moment to obtain this answer. Here I show the results, so we can see niobium oxide. This is result of this vote, so it was a good point. And the same analysis is the conclusion. The proposed route, so avoid the acid use acids. The boric acid improves process efficient. The liquid-solid ratio is critical for water solubilization, and this formulation contains 6.8 of sodium carbonate and 12% of boron acid, and 20% of the columbite present the best result. This is just a flow chart, so the process: columbite, fusion, separate magnetic, water solubilization, precipitation, and calcination. It's just it. I think it's my time. Hamilton.
Yeah, thank you so much, Eduardo, for your presentation. We have a lot of questions we can talk later. So for the last presentation, I will present in behalf of Dr. Carlos Opa. So Dr. Carlos is having some troubles in terms of internet connections. So I'm going to present in his behalf. So his presentation is focused on rare earth elements from unconventional sources. So here today we are listening about niobium, steel making waste material. Eduardo, I think you are still sharing your slides. Just check that. Thanks. I think everyone can see my screen here. So, and now first presentation was about steel making, iron steel waste, and then we had Professor Eduardo talking about niobium. And now we're going to talk about earth elements because all those materials are critical metals and they are really important for energy transition, as we said before. And we are looking for, and we are working, all of us here are working, developing process, chemical reaction, improving chemical reactions to recover those critical minerals from all sources as much as possible towards sustainable mining, sustainable process. And rare earth elements play a pivotal importance here in this process, since those materials have a market control from only one country in the world because of resource, technological development, and we are looking for different source for domestic supply chain, domestic production as well. So, for example, rare earth elements extraction was developed in US, here in US at Columbia University, and then was upscaled and put in a commercial scale in China for many years. Also, in China, in the country, there are a lot of production of materials, technologies that require rare earth elements. So that's why it's so important rare earth elements for the Chinese government and Chinese companies, because they are using to produce electric vehicles, smartphone, laptops, and so on. So that's why the market is improving. And also to reach the energy transition, we need even more rare earth elements. So that's why we need to find source from what we call as unconventional source. And here, Dr. Oba work was developing and making characterization of different sources in Brazil's soil. Brazil is one of the most important players in rare earth elements market as well. So just for a few data in terms of what is the rare earth element source in China, not only primary source, for example, mineral reserves, production, refining as well, but also for production of magnets as well for different equipments. And in terms of Brazil, as a Brazilian, I can say we should be really proud about our mineral resource. And Dr. Oba making here in this slide a really good presentation about stating how much resources we have available in the market, in the soil, sorry, on lands to be mining, and how much production we can achieve if we achieve a really good development, technological development, and upscaling the technology. So we have some challenges here for our elements. For example, process, low efficiency, high pollution process as minerals processing used to be. But also we have a really great advantage in terms of deposits. We have a lot of deposits. Brazil has a lot of really good deposit, important deposits of rare earth elements. And here we are presenting the recovery of rare earth elements from phosphor and niobium mining waste, as well as important resource. So, for example, Professor Eduardo was talking about niobium from Columbia, but also we have rare earth elements from those sources as well. So we should explore and should have more information, more details, not only from niobium mining waste, but from phosphor materials. And the main mineral of interest is monazite. It's a phosphate mineral containing cerium, lanthanum, yttrium, and thallium as well. And it's one of the three most important mineral of interest in the world as source of rare earth elements. And the reason for why you are looking for unconventional source is because we are having a depletion of deposits. So the grades of the ongoing mineral deposits are decreasing over the years. So in Europe, there's a really good discussion about deep sea mining, for example. It's because we are looking for new types of source. However, there is a high cost for research and mining for new deposits with high grade for extraction. And we have problems, as we observed in Brazil a few years ago, in terms for mining accidents from tailing piles accidents, and also high environmental impacts. So if we're looking for a different resource of critical minerals, we can decrease the strong dependence we have right now from mining from mining extraction, mineral extraction. So, for example, as critical minerals resource, we have here battery recycling. So if you're going to have energy transition from transport sector, we are going to have a lot of batteries available in the market that we should recycle. Electronic waste, everyone here is watching this webinar from a laptop, smartphone, on TV, and all of those are electronic equipment that in a few years you became electronic waste. So we should recycle and promote circular economy as well. And it's like recycling because as we saw in the first presentation, we are generating a lot of materials with high concentration of those critical minerals as well. So here are a few examples about unconventional sources that we have also, and some factors about to reach that technology or reach that goal to recover critical minerals from unconventional source. So we need developing new process, new products, right? We still depend on the price of metals and minerals in a global level, so it's not so simple. Costs of the process and use of semi-processed materials for the process. So here are some examples of a really good Carlos Coba work about making a characterization about the process, about some materials available in Brazilian soil for containing rare earth elements, one of the most important, maybe one of the most important critical materials. So for example, here, take a look at different fractions of those materials. We have concentrations varying from 1 to 2% to 11% of rare earth elements oxide in an oxide form, which is really good because I remember during my thesis, I was working with scanning extraction from bauxite residue, and I was working with a few ppms of scanning and rare earth elements. And in Brazilian soil, we have a high concentration of those rare earth elements that justify the extraction process and pay the costs of the process, and then we can mine on land as well, rare elements. Here is another example varying the proportion, the composition, the fraction of from different fraction of the soil. And the challenge indeed is the silicates, the presence of silicon, iron, calcium is also a challenge as well. But when we take a look here, the concentration of rare earth elements, we can see that we have a really good source, not only of critical minerals for global supply chain, but also to create new jobs, new technologies, developing new technologies, and create more profit in your own country, in your home country. Here's some more data in terms of about the particles, the average diameter of those particles, those materials, and distribution of those samples. And indeed, monazite is the most important in terms of rare earth element source, rare earth elements, the presence of rare earth elements. And quartz and barite are also a challenge for chemical process or thermal process. But here we can find about 24%, 28, even 30% of monazite concentration in the source. So some mineral liberation analysis for those samples, and we can also check that monazite particles are separated from barite sample as well. That means we can do a physical separation and even increase the concentration of rare earth element of those samples, which corroborates with the previous analysis, with the previous tables that I just showed you here. So here are some pictures about those samples. I love those SEM analysis. We can check about the composition and we can predict and simulate the further process for extraction of rare earth elements. So here it's a really good work from Dr. Carlos Zoba. And I'd like to thank not only to be here with us, but also share this presentation. And indeed, as a final conclusion, partial conclusions about this work, we have there are monazite minerals in final fraction that makes even better for chemical process for production of rare earth elements, and effective liberation in about 0.15 milliliters of particle size. And also due to porosity, monazite does not respond well to gravity concentration method, so we can go to another kind of physical separation, which means it's good for upscaling the technology and achieve TICO. So we have some possible concentration. So just in terms of time, I'm gonna finish here the presentation. If Dr. Carlos Oba is having some international issues, so that's why we're presenting in his behalf. But he's open also for answer any questions from the audience. So here I'd like to finish the presentation from the panelists. And I'd like to open the floor for questions, and would love to answer the questions. So I'd like to give the opportunity to talk of Professor Rogério from PUC-Rio. Professor Rogério, do you have any questions?
Thank you, Hamilton. Yeah, indeed. I have some questions for maybe one or two questions for Gabriel. Gabriel, thank you very much for your presentation. So the first one, considering, Gabriel, the Brazilian scenario, yeah, for exploring this type of technology, what metals would you believe to be the most promising to maybe to develop a market on these metals, to explore them actually in an industrial scale? Yes? Could you
Yes.
then
Uh,
say something about that, please?
Indeed, what we have is an international market. So Brazil is already included on this, and mainly aluminum and copper. I would say it's
Copper and
the
aluminum.
most common metals. Okay.
Oh, yeah. Okay. Indeed, very important and critical metals, yes, for many applications. And only one question more. I found that I didn't know that this type of physical separation method that you introduced to us, the current method, I found it very interesting. Could you say to us something about the selectivity associated with that metal? Because yeah, we you all know that metals can conduct very good electricity. So actually, I was a little worried about the selectivity, or which level of selectivity could we reach in this with this process? Could we separate very good the metals involved, or yeah?
Yeah,
Or in the end, we have
it's
a mixture of metals and we need some other process later to try to extract them
yeah.
and separate them.
It's a challenge for the technology. Of course, the iron was separated by magnetic, so it's okay. But the other metals, you're right. You have a mix depending on the scrap input.
Okay.
One thing is, as you separate by size, maybe there is a tendency to have some metals on the finer sizes. And you have a typical composition of this co-product. But thinking about roadmap, yes, to improve the post-separation methods, for example, hydrometallurgical for electronic separation, and density metals to post-separate other metals, it's a good roadmap to make this material even more valuable, because that's the point. The industries in general and the researchers are trying to make these materials more pure and the price even better.
Okay. So it could be an interesting field for further research, yeah? To
Yeah,
stimulate further
exactly.
research activities in order to try to couple this adequate metal with some other, maybe hydrometallurgical or chemical routes. So thank you,
Yeah.
Gabriel. Hamilton, these are my two questions. Don't know if
Thank
you
you so
have.
much.
There was a question maybe in the QA box,
I can
I
handle
think.
that, don't worry. Yeah,
Okay,
I can
thank
check
you.
that. Thank you so much. I'd like to bring one question to Professor Eduardo. So, Eduardo, thank you so much again for your presentation. It was really clear about your work. And indeed, work with niobium is a challenge for several reasons. We can talk days or years about that. So regarding the flow chart you presented, I was wondering, any thermal process has a challenge about the energy consumption and the cost of the energy consumption for the reaction. Did you check on that? And can you tell me a little bit more about what kind of questions are you looking for to answer about the process, and what kind of challenges you see for the future of your projects?
Okay, thank you, Hamilton, for the question. The point is, we try to develop a process without strong acids or strong bases. For example, high chloruric acids or sulfuric acids. This was the main point for us. Okay, I know that my route, this route that I presented, uses high temperature. For example, 9 degrees 100 Celsius is high temperature for the process. But we don't have the problem with the environmental problem, because we don't have how can you say, how I say acid used, and for example I forgot the name in English. Sorry.
You can say in
Uh,
Portuguese and I can translate if I know.
Okay, ammonia.
Ammonium. Yes, it's ammonium. Yeah.
Ammonium. I forgot the name ammonium.
Yeah, that's fine.
These are I saw a lot of routes using these here components. So it's dangerous for the environment. About the energy, we don't make a deep study about this yet, okay? But the goal of this project is just to develop a hot with free strong acids and strong bases, okay?
Well, that's interesting. So based on what I know about niobium extraction, using this kind of material for thermal reaction, you were reducing the temperature for the thermal reaction. Is that correct? Lithium borate, I think you're using for your
Boron,
reaction. Yeah.
boron, yes.
Oh, yeah. So what is the gap between using and not using this material to decrease the temperature? My question
Okay.
is, if you not use this material, what is the temperature required for the reaction?
Okay, for example, the melting temperature of the sodium oxide is about 140,000 degrees Celsius.
Wow.
So you can decrease it for 90 thousand, 100, sorry, degrees Celsius. Decrease a lot.
Okay, that's great. Thanks. Before I continue on K&O section, K&O part, I have a question to Gabriel. Gabriel, in Brazil, we have a lot of knowledge for recycling of those materials. Why we are still working to create solutions for this problem? So, for example, Professor Eduardo have been working on this kind of topic before. What do you think? What do you think are the questions we're still trying to answer, and we are not reach that goal for recycling this kind of material? I don't know if my question is clear.
I'll try to answer. One thing I guess it's the scrap market is not so refined as the steel making route itself. So we have to deal with very mixed materials. So one challenge I would say is to increase the yields of these processes. For example, I showed you a flow chart where we had 1% 0.8% of non-ferrous recovery.
Mhm.
It can reach, for example, in some shredders all over the world, until 2% of recovery. And it's basically because the scrap separation
Mhm.
and the improvement on the technology also. So this is the key factors. As we know well how to process, but we have to make it more efficient year to year.
Oh, I see. I see. Okay, thanks so much. So one of the questions we have from Q&A to here is what is the relationship between monazite and barite and apatite? I think that's related to Carlos' old presentation that I had the chance to present his behalf. So those minerals are they are found together in this kind of source that we call as unconventional source. And that's interesting for this work is those materials, monazite, barite, and apatite, they have different compositions. So monazite is the main one related to source or the presence of earth elements. And barite and apatite is rich in calcium, for example, and those doesn't have the presence or maybe in a really low concentration of earth elements. And indeed, what is found in these studies, those particles are separated, physically separated, which means that if it's possible to make a physical separation in a large scale, that means we can have a higher content of solid material of monazite with earth elements. So in terms of what is the different of those materials is in terms of composition, and the relationship is they are found together. So there are more difference than connection among those materials. So thank you so much, Amina Ali, for your question. That was a really interesting question. I'd like to open for more questions. So from Kushi, I need some help to find his questions. If someone can help me, maybe I lost somewhere. Sorry, go ahead.
Yeah, so the first question from Kushi Madan was
Mhm.
what will be the future aspects for this? And I think this question was meant to be for Gabriel. So if we can ask Mr. Gabriel to answer the question, what will be the future aspects for this?
For these projects, maybe it's related to the question to the project itself. So Gabriel, are you still with us?
Yes,
So
I'm here.
can you tell us a little bit
Yeah.
about the future of your project? What you are thinking about the future of those points you highlighted?
What's the crucial points, as I told to Rogério, is to work on the post-separation methods. As it's a mix of non-ferrous with aluminum, copper, and electronics. And sometimes we have also hand picking stations until nowadays. So we have to improve the methods and technologies to post-separate these metals. And of course, it makes the price better on the market also.
Mm-hmm. Yeah, that's great. Thank you so much. There are a lot of challenges also related to market, not only technological developments, right?
Exactly.
Yeah, that's why engineers working so hard and we are spending a lot of time and brains on those questions. Yeah, that's why we need a really good interdisciplinary group of people working on those challenges. Okay, so let me check if you have any additional questions.
Yes, there's another one from Kushi,
Mhm.
and I think that was to Eduardo, Professor Eduardo Junca. And the question is for niobium oxide as solar cells. Also, do we have an alternative?
But the question, Eduardo, is in terms of solar. Let me read it again here. Let's go back. Okay, so for niobium oxide, do we have any solar cells made by niobium oxide? Do you think it's a future as well, or do you see like that?
Uh, well, let me see if I understand well. The niobium oxide, I see it's a metal for high technology points, structures, and one of these is about this point. I don't know if I understand well. The sound is not good for me, Hamilton. The sound is not
Sorry,
good
say,
for me.
can you hear me now? Is that okay? Can you hear me?
Okay.
Yeah, so sorry, can you repeat that?
Okay, I didn't understand the question well. This sound from these
Mm-hmm.
pessoas. Oh,
No, that's okay. I'll repeat that, but the question is more related. If you know something about the use of niobium oxide for solar cells, have you seen something like that?
no, I don't study about application of the niobium
Mm-hmm.
oxide. It's just for extraction of niobium, okay?
Mm-hmm.
But I know the niobium is a good metal for application, high technology applications. For example, in solar cells, aerospace alloys, for example, or for example, a new project here we are starting now is using niobium to produce aluminum niobium alloy. We just
Mm.
started to this this idea. We
Mm-hmm.
have
Mm-hmm.
another research with Professor Mateus. I think you remember Professor Mateus
Yeah,
from
yeah. Mm-hmm.
he worked with polymers. How to say polymers in
Polymers.
English? Polymers.
Polymers.
Or make a semiconductor semicondutores. I forgot his name.
Semiconductor. Yeah, that's pretty much similar.
Materials.
Yeah, don't worry.
So we have a lot of ideas to use
Mm-hmm.
the
Mm-hmm.
niobium, but we need people to study this.
Yeah, so
So
if you're looking for a PhD in Brazil, you should reach out Eduardo, Rogério as well.
I open here. We have
Yeah,
scholarships. We have space. We have a
they
good.
have,
We have a lot of equipment.
and the city
So
is great as
I
well.
mean,
Okay,
yes, it's
we
a
should
good
not
city.
compete. We should not compete with Rio, but it's a different topic. Okay,
Okay.
so we'd like to finish this webinar. Thank you so much for your presence, for the audience, for all those outstanding questions. I received a lot of questions in my personal message as well. So, as I said, we are open. We have this special issue open. So the best papers we receive, we are going to deliver 100% discount voucher. We don't have a lot. We have just a few. And if you are interested to submit a paper, you can reach out me, you can reach out Rogério, and please contact Agnieszka as well from MTPI. They are doing outstanding work and helping us a lot. So I'm really glad to have this team from MDPI, from Minerals Journal, to helping us because we cannot do all this job without them. So, Rogério, a few words before we finish.
Yeah, Milton, thank you very much. Okay, I'd like to thank all the scholars, for all the presentations. I think that we are dealing with a topic which is, as I said in the beginning, vital for the future of the mankind. In our planet, we are facing very, very big environmental problems, and I think that through recycling is a way to try to minimize these impacts. And the way is open for very interesting new processes. I found that, for example, the process that Professor Eduardo showed us was very interesting. In the sense of the chemical, the coupling of my physical and chemical processes. And so, as I said, we have already achieved the state in that we have accumulated a lot of knowledge in regard to phenomenological modeling of these processes. So, and also the characterization tools they have evolved. We can characterize, we can evaluate the chemical composition of these typical non-metallurgical sources. And this is a very important point also. And yeah, we wish that maybe people here that will listen to us could contribute to this special issue. We welcome all these contributions, and we hope that we can have some very good papers to work with them. Yes, thank you, Agnieszka. Thank you, Hamilton, and all of you.
Yes. Thank you. I would also like to say a few words to finish this webinar. I'm very happy that we've organized this session to talk about this very important topic, and I would like to extend a very nice thank you, a big thank you to the chairs of this webinar, to Dr. Botello Jr. and to Dr. Navarro, and also to the speakers for your presentations. Thank you very much. And of course to the attendees that came for these presentations and for the questions. I hope that we will have many other opportunities to organize webinars like that with minerals. Thank you very much.